Okay, good evening, everybody. Welcome to the fourth in our series of the AIT Spin Professional Intelligence Master Series. It's my pleasure to welcome Dr. Ahmed Hammad, who is our guest speaker, our expert tonight. My name is Dr. Roger Levermore, and I chair these sessions. The structure or the format for this evening is where I provide a little bit of information about what AIT Spin, the Professional Intelligence Program, looks like. And then we have about 30 minutes for presentation by the speaker, and then that's followed by a Q&A session. So I look forward to the next hour with you and with Dr. Hammad. Just starting with a quick word about the programs that we run at AIT Spin. There are two different versions of that program. We have the Masters, which is professional in professional intelligence, and then also an executive certificate, which is a smaller amount of credits that relates mainly to the data science spine. So we have those two different offerings. The overall focus is about embedding AI into many parts of our work and our lives, and to go through and take a step back, think about the application, but also about some of the pros and cons of that. So this is the ability to bring the kind of expertise that you see this evening with Dr. Hammad, looking at making those who join the program more fluent, but also have a more critical sense of the use of AI, so that working professionals that are taking this program stay effective and adaptable and therefore valuable as things change around them. So this essentially is for working professionals who carry on in work, but they want to go through and enhance their capabilities, looking at AI. The Professional Masters Program is structured with 36 credits, and that's in three parts. The first part is this AI spine, which is looking at different aspects of data science, such as data reasoning. And then you build around that in different clusters that you can choose, which might relate to machine learning, might relate to sustainability, could relate to business and finance or design thinking. So that's the first part of the program. The second part is the specialization buffet, and those different streams relate to any of these topics on the right-hand side. This is where people might want to get a deeper level of knowledge in public policy or climate or different aspects of engineering. And every single course throughout this program, including the specialization, has woven AI into it. So that's the second part of the program, the specialization. The third part is where you complete the program by looking at a capstone. Sometimes this will be related to where you might be working. Sometimes it's sponsored by your employer, and that's for either 6 or 12 credits. This is all completed by what we call high flex. That means that classes take place outside of normal work hours, and students have got between 1.5 and 5 years to complete. So who is this program for? Well, these are the type of people who have signed up to the program, which starts next week. We have working professionals. We have managers, those that will be leading in the future. We have a healthy amount of applications from people with a more technical engineering background. We also have some entrepreneurs who are trying to work out how can they use AI for their startups or for their new companies. Then we've also got applications from people from the development and public sector background. Sometimes they come through from companies which are they're paid for by their employer, and sometimes we get recent graduates. So the age span and the experience span is really anything from 23 to 66 years of age, all of them working professionals. In the first of the expert series, we were asked the question about what makes this program different. So for me, there are four key areas. Number one is what I've mentioned about the high flex, that this is about completing it at your own pace and also in your own style. So if we have some lectures which will be in person, but the students will join either in person or through the live online class, or they can watch the recording of the class afterwards. Some of the sessions, the lecturer might be based in Hong Kong or Singapore or other countries, and that means that that particular class will be entirely online. So Hyperflex is the first selling point for the program. The second differentiator is where AI knowledge and tools and application is embedded in every single course that a student takes across the program. The third area is that everybody does the kind of the spine, the data science spine at the start, but then after that, they can go through and specialize in a particular track that I mentioned in the last slide. And then fourthly, the people who are teaching on this course are experts from industry. They might be AI experts and academic experts as well. So we have a nice blend of different international faculty that will be teaching across this program. Where do we see people going after they have completed the program? Well, we feel that some of the roles and the moves that people could make is maybe continuing in their own job, but they might lead AI-enabled change or transformation. It might be bringing AI into their own specialist area. It could be looking at the execution of AI from more strategic overview. It could be about thinking how can they build their own AI agent to help them to make them more productive, more effective in the workplace. Other upskilling areas that you would expect to see here is people being able to use AI tools fluently and critically, but also responsibly. And then how do you communicate the big advancements and the changes within AI across technical and non-technical teams? So we see these two areas being a vital part of the program and the type of things that a student will get when they graduate. So the main focus is to stay valuable and promotable as AI reshapes your field. So that's the introduction to the AIT School of Professional Intelligence and our two programs. It's now my pleasure to go through and introduce Dr. Ahmed Hammad, who is going to be talking to you today with a background in causal machine learning, which he earned his PhD in. Dr. Ahmed has work which is kind of spanning the private sector, academia, education. He's looked at industries which include healthcare, environmental monitoring, and disaster preparedness. And he has taught data science in Australia, in Singapore, in Indonesia, and in Malaysia, and currently based in Bangkok. So I'm going to stop sharing my slides, and I'll be asking some questions at the end of Dr. Hammad's talk. But over to you, Dr. Hammad.
Thank you very much, Roger. Thank you. Thank you. So I'll be sharing my screen so we can start the presentation. All right. So first of all, thank you. It's such a pleasure to be here and have sometimes to share, talk about a topic that is very dear to me. And I would like to bring your attention on the title, first of all, Decision Making for AI, and not AI for Decision Making. This is not a typo, this is on purpose. Most of the talks out there are mainly focused on highlighting how AI can help you take decision, how AI can take decision for you. But today I want to try to bring the thing the other way around and focus on empowering us back, okay, when it comes to take decisions. So by the end of this presentation, my goal is that you will be able to distinguish what is correlation and causation, the difference between correlation and causation, and why this difference matters so much for decision making in AI. Understanding why AI trained on what we call observational data, okay, can produce systematically misleading conclusion. And what human reasoning can contribute. Okay, so this is really our contribution, and this is something that the machine, by definition, cannot do. And more in general, reflect on the methodological responsibility that I believe every one of us has when using AI to inform real decision. And this applies on any kind of discipline. And finally, this is another very important aspect when using all the tools around AI, statistical algorithm, machine learning algorithm, and so on. Understanding the assumption and limitation of each tool. Something that I like to say very often is each tool has its own limitation, its own assumption, and they are part of your toolkit. So you need to know every single aspect, every single piece of machinery that you can use to tackle a certain problem. So I'm gonna start with a question. So what can you do that AI cannot? I'm gonna guide you through my process, okay, of thinking about it. How would I answer this question? And later on, at the end of the presentation, I would be happy to know your answer to this question. Right? So first of all, before actually trying to answer the question, what I would do is that I would ask myself what actually AI is good at, right? So we can all agree that AI is extraordinarily good at doing one specific thing, and this is finding patterns in the data, all right? Give it 1 million of data points and we'll find all sorts of relationships that human could never spot manually, all right? And this is very powerful. This is the main power in AI. And again, I'm going to use AI in a very broad, I'm going to use the term AI in a very broad way. I mean, statistical algorithms, machine learning algorithms, ChatGPT, LLM, and so on, right? But let's look at an example when things could go a bit in a different way. So here we have a classic example. Those are real data. We have, on one hand, we have ice cream production. And on the other, we have drowning deaths in the US, monthly averages. If we look at the panel on the left-hand side, we can see that the distribution over time, over the year, of the two variables is basically almost perfectly overlapping. And the same information is conveyed by the plot on your right, in which you see the correlation, right? So you see that as one goes up, also the other one goes up, right? So based on these numbers, based on this analysis, one might be tempted to say, you know what? Should we ban ice cream to prevent drownings? Some of you obviously reading such a question, they are either smiling or they are just thinking, this is absolutely nonsense, right? And I agree with you. But the thing is that if you were to give this to a machine learning algorithm, to an AI system, based on this data, the model will see what? Will see a pattern, all right? The thing is, the pattern is undeniable, okay? The pattern is real. But the assumption behind this question, it's something that goes beyond the pattern. The assumption behind this question is there is a relationship between ice cream and drownings. And hence, if we were to stop the production of ice cream, we will also stop the drowning deaths. Also, this assumes that there is a causal relationship in the sense that ice cream, okay, the production of ice cream causes the drowning deaths. Obviously, this is absurd, but it helps us to see something very important. One thing is to learn or capture patterns. Another thing is to learn relationships. And as you can guess, relationships are far more important than patterns. Also, this allows us to try to go beyond the observed pattern and ask ourselves, like, what is going on? Why the variables are behaving in this way? Why I see this pattern? Well, most likely, you're not seeing the full picture, right? So there must be a third variable, in this case, temperature, summer heat, that is driving both. And this absolutely makes sense. So this allows us to introduce three important keywords: correlation, causation, and confounder. Correlation is what we have observed earlier, two things moving together. Causation, on the other hand, is one thing producing the other. And finally, we have confounder, which is a hidden variable, okay, that can explain the observed pattern, okay, and break this assumed relationship, this false relationship. Let's take another example. Here, it's a very beautiful example from a very interesting field in AI that is called explainable AI. For those who might be new to machine learning AI and so on, you can imagine that there are so many algorithms, so many ways of learning from data, right? Some of them are simpler, some of them are more complicated. And usually there is a very interesting pattern in this type of algorithms is that the simplest one, we usually call them white box model, because they are simple, they do not provide very good results, but they are transparent. We can understand how that algorithm, that model is taking a certain decision, right? On the other hand, we have very complicated, extremely powerful algorithms, such as you might have heard neural networks, the underlying algorithm behind LLMs, ChatGPT, and so on, that are extremely powerful, but they are black box model. We cannot really understand what's going on inside of them. And obviously, we have been trying to solve this problem, maintaining a high prediction power, but in the same time, finding ways to open those black box, right? And explainable AI is exactly doing this. Here we see a beautiful example. We are talking about image processing, image classification. We trained one of those complicated algorithms, a neural network, to classify, to learn the patterns in the pictures of wolves and huskies. We trained the model and now we want to test it, okay? So I'm gonna provide few pictures to the model and see what it's gonna predict. So as you can see, starting from the left, the first one was predicted wolf, but actually it's husky. The second one, husky, husky, and the third one, wolf, wolf. So far, so good, in the sense that at the end, we made only one mistake. It would be better, obviously, to use much, much more data, right? Test it with more images and then get a kind of a number of the accuracy level of this algorithm. But the point that I want to focus on is something else. So I observed this, and my question here is why the first one is wrong. Explainable AI, and the simple fact that we're asking ourselves why the first one was predicted wolf instead of husky, it's so powerful and it's so important because it can help us to debug an algorithm. So look, for example, at this. So this is the result of applying an explainable AI algorithm to our original model. And when you see it for the first time, it might be a bit confusing, but actually what you see here is what feature, okay, what part of the picture drove the decision of the model at the time of prediction. So in this case, we see that when the prediction was wolf, okay, when the prediction is wolf, the pattern that is driving the decision is, guess what, is the background. So this is so interesting. So the model is saying all the time I see snow in the background is equal to wolf, and I'm gonna predict wolf. Obviously, this is something that doesn't make any sense for us because we would expect the model to learn some pattern related with the animal itself, but instead it's learning the background. So we see how explainable AI, we see how asking ourselves why we got this output, it's so important and it's so powerful. Now, these results could be used, first of all, from a purely technical perspective to debug the algorithm, right? But you can imagine how you could extend this approach to answer any question regarding any algorithm in order to understand what are the driver behind your decision. Again, we see the same issue as before. The confounder in this case is the background. The model found a pattern, okay, a pattern that was mainly due to the data. So most of the data, most likely, why we see this pattern, most of the data in which there were that were labeled as wolves, pictures of wolves had in the background snow, and that's why the model found this pattern and just ran with it. Let's take a third example. And this is another very interesting example because when we're talking about healthcare and AI, we're talking about very sensitive data, very sensitive topics, right? It's a controversial application of AI sometimes, right? And imagine there is an hospital which decide to um, train an AI system to get a suggestion, okay, a decision regarding which patient should receive an aggressive treatment. Please pay attention on the term aggressive treatment. This is the most important thing. So the AI is trained with all sorts of historical data. So they have massive amount of data, whether the patient received the treatment, whether the patient survived, gender, age, body mass index, blood pressure, whatever, okay? All sorts of variables. And we get something like this. So when the model is looking at the data, we are dumping the data in our AI system. And the first thing that the algorithm notices is what you see on the left-hand side. So we see that we have most of the individuals that were treated, sorry, had a higher mortality rate. So they are more likely to die within 30 days after receiving the treatment. Obviously, the algorithm will recommend do not treat them. But if we go beyond this first layer of information and we look at the severity group, and this is what we see in the right panel, we dive deeper in the data and we find out that actually the treatment was helpful, especially for those in the moderate and severe group. So this is an example of something known as selection bias and Simpson paradox. Okay, so basically when you look at data uh, on a certain scale, okay, grouped data, you get a certain picture, but then when you dive deeper in subgroup of the population that you are analyzing, you get completely a different picture. But the goal here is not to show you the Simpson paradox, but something far more important. So I told you earlier to focus, okay, that the most important keywords are aggressive treatment, right? So the sickest patients were the one who received the treatment. And of course, by definition, they were the one with the worst outcome. So they were already critical. But why is that so? So the AI again saw a pattern in the data. Okay, if you give the treatment, people tend to have a higher mortality rate, but it could not see the selection process that created the pattern. So this is another important point when we are dealing with machine learning and we want to go beyond patterns. So the selection process, it's something that relates to what we call data generation process. So how the data that we are observing came to be, right? And this is something that is not something that you can read in the data because it's the way in which the data themselves were generated, right? And the machine in this case could not ask again, why were those patients selected for the treatment? And here we see a beautiful thing is that there is a massive assumption behind this data. And it's not only an assumption, it's a pillar in healthcare that an intervention is justified when the potential benefit in severe outcomes outweigh the uncertainty risk of the side effect. So this rule is embedded in every hospital, every intervention, every medical decision, right? And so it's not something that you can see or read in the data because the data were generated based on this assumption. So again, understanding the cause, asking yourself why the data came to be, okay, are what they are, it's very important. And again, a machine learning algorithm, an AI system, an LLM cannot answer this question, cannot even ask itself this question. So this leads us to an important point. One thing is statistical learning. And by statistical learning, I mean machine learning, any statistical algorithm, LLMs, even they are just statistical algorithms, is different than causal learning, okay? So statistical learning asks the question, what can I predict? Causal learning asks, what would change if I intervened? And when we're talking about business, when we're talking about decision making, what we are interested in is not about a prediction, okay? Predicting something really well, okay? Having a highly accurate prediction, but we are interested in changing. We want to change something in our environment. We want to improve our business. We want to make more money. what do we need to change, okay, in order to achieve that goal. And to learn what we can change, we need to understand the causal chain behind the phenomenon we are studying, right? Another important point, as you can see here, is that a highly accurate predictor does not automatically identify a causal effect. Actually, we could use a very simple model if we have the right methodology, if we have a clear understanding of how the data were generated. If we go, so far we have been looking at statistical model, machine learning algorithm, but if we talk about LLMs, large language model, ChatGPT, and so on, it's the same thing. Okay, so research shows that LLM struggle with the true causal reasoning. Okay, so and why is that? Again, we need to ask ourselves how those algorithms were trained. What is the data behind them? And as you might know, LLMs, they are nothing else than very advanced algorithms. They are just designed to predict the next token, the next word. And they are learning patterns in human written data. So they are finding correlations, okay, in human written data. And pay attention, again, we are talking about patterns and not causal mechanism, right? And this is obvious because most of the time we use the term correlation, causation, or even when we are talking about something causing something else, we can easily use the same terminology, okay? The way we write it down, the way we explain it, it's very, very similar. So it's impossible that an LLM can learn through causal reasoning, right? This leads us to another issue that if you have been using ChatGPT and other types of LLM, you must have experience. What we see as knowledge is just a byproduct of the model being very good at predicting the next token in a sentence. So those models are not designed to provide you with knowledge. The knowledge that you see in the text, well written, okay, and it looks so professional or it's so detailed, it's just a byproduct of the model being very good at predicting the next token. But again, it's not knowledge. Let's take an example. Let's say we ask to an LLM employees who took our optional training score, our optional training scored 23% higher on their performance review. Should we make the training mandatory? So we give some data, or we just mention this to an LLM, and the answer of the LLM could be very likely like this. Yes, the data show a clear 23 performance gain. Making the training mandatory would extend that benefit across your entire workforce. So this sounds absolutely reasonable. Absolutely reasonable. If I read it, I might be tempted to say, yeah, it's correct. Actually, this is very fluent, very confident, but it's absolutely wrong. Why is this wrong? Well, the people who chose the training were already the motivated ones. So here we are observing something that is self-selection. If you were given a training for free, for example, and you are not forced by your company to join it, okay, those who will join it are those who by definition are more motivated, and of course they will have higher scores. You follow what I mean? Like, this is a very important point. Like, just in the text, most of you might be tempted to answer exactly in the same way the LLM have answered this question, but actually this is wrong, okay? So far, I've been highlighting the pitfalls, okay? So many negative things about machine learning, AI, and so on, but let's go back to us, right? So are we really that good? Well, honestly, we're not really that good. Like, causation is hard for humans too. We confuse correlation and causation all the time in medicine policy, in our relationships with our family and friends and so on. So what is actually the difference between us and the machine at this point? Well, first of all, I would say that we know it's hard. And this is a very important point because we know it's hard, and that's why we have developed approaches, methodologies, methods to go beyond our limitation. And here we have, for example, randomized control trials, so the so-called clinical trial in health, A/B testing in marketing, the scientific consensus, the legal standard of proof. It's another beautiful example. Imagine that you are in front of a burning building. You're there alone. At a certain point, people arrive after you, and guess what? They will all point their fingers at you and saying that you are the cause of that, right? You are the reason behind it. That's why we have the legal standard of proof, okay? Because it might be that this is just a pattern. You were at the wrong time in the wrong place, and that's it. You're not the cause. You're not the one who end up burning the building, right? So again, we know it's hard, and that's why we develop methods to go beyond our limits. Another thing, and this brings us towards the conclusion of this little webinar and time together to share a bit of my about my perspective on this, is that the most important question, the question that changes everything, and this applies to, again, every field, is asking yourself why, okay? Remember that correlations tell you what the world looks like, but causation tells you what you can change about it. And again, as I said earlier, we are always trying to change something in reality, all right? We want to go beyond patterns and find real relationship, and being able to change, play with those relationships in a way that benefits us, right? What can you do that AI cannot? So my answer to this is, first of all, you can ask why. And beyond that, you can suspect a pattern and say, something feels off. Let me find the mechanism, all right? You can sit with uncertainty, and uncertainty is such an important word, especially nowadays. Remember that the most dangerous thing about AI is not that it's wrong, okay, but it's that it's confidently wrong in ways that it cannot detect, okay? It cannot detect. It would be really nice, let's think about, for example, LLMs, right? When you are talking with the ChatGPT, and imagine that for every answer you get, you would find a little number attached with it that goes from, say, from 0 to 100, and it's quantifying how confident the LLM is with that given answer, right? That would be so nice. While statistically speaking, mathematically speaking, is possible, it would be extremely computational intensive, so you don't see this. But again, uncertainty is something that we have been working so hard to get rid of. And now with the explosion of LLM and AI, we are really just giving away this uncertainty. We want to get rid of it in all sorts of ways, while actually this is so important. It's so important to doubt, okay, and to build on top of our doubts, because it's our doubt that allow us to go beyond observed patterns and really understand what are the true relationship behind the data that we're working with, behind the challenges that we are facing. Thank you very much.
Thank you very much, Ahmed. And there's lots of nuggets there of information that I'm looking forward to asking a few questions about.
Sure.
The audience too have got the opportunity to ask questions, mainly through the Q&A box on this webinar function. But while we wait for any questions to come in, maybe I'm curious about two things initially. And if you can stop sharing your slides, that would be great.
Yeah, sure.
The first is how did you get into this initially in terms of your whole interest in LLMs? How did that begin? When did it begin? And
My interest in
what was the motives behind it? What is it that you started you on this journey?
Oh, well, that's an interesting question. Well, I think I've been always interested in, I've been asking myself why since, like, very often, okay, since I was a kid. I found out about statistic back in the days, and I was like amazed by it, right? Like all this order, right? At the beginning, that's the first thing that I think amazed everyone. Uh, all those tables and everything was structured, and the fact that you can learn from that, I felt like I could somehow look at the world and make sense of everything and take decision on top of that. And obviously, this went from classic statistical algorithms, learning about patterns, and then more and more into causal inference. And then, okay, I need to know more about fancier algorithms, stronger algorithms that can help me to really estimate the effect of this intervention, this public policy. And then, I really worked in several fields, like public health, environmental data modeling. This is something that really pushed my knowledge to another level. Back in the days, like it was the boom of satellite data, and so much data to work with, so much fun, right? and we could, you know, extract hundreds of years of data, daily data from everywhere, look at things directly from the sky, and then we could see how humans are interacting with each other, like government policies and so on. We could look at the effect, estimate the effect of those policies using machine learning, econometrics, statistic, defining the methodology. I think it's a very elegant way of learning from data, and that's what really attracted.
That's great because that leads on to my second question is that
Yeah,
you do this in healthcare, you do this in environmental monitoring that you've just mentioned, and also disaster preparedness. Maybe just
yeah.
a few words about some of the projects that you're involved with.
Yeah, thank you. So I've worked a lot into environmental data modeling, mainly related with the climate change and policy to increase the resilience of countries which are heavily affected by climate change. Healthcare, I worked in healthcare optimization. So, for example, allocation of resources, clinics over all sub-Saharan Africa. And I use a lot of satellite data, Google data, layers and layers of data. This is what you can do today with big data, right? You just keep on adding layers and layers and layers and layers of information, and you can really construct scenarios and optimize all sorts of things in a very useful way, right? So, for example, for this optimization, we were trying to make sure that people on all over all sub-Saharan Africa could reach a hospital or a clinic depending on their needs within a certain amount of time. All right. So we had friction data, distant data, Google Maps data, all sorts of things. And now I've been working a lot into I've been focusing mainly on the integration of AI in official statistics, governments, companies, how to use it the right way, okay, how to allow every company, every organization to really leverage AI while keeping them safe from all the issues that might arise when it comes to liability, responsibility, hallucinations, and so on.
Good. I'm just looking at a message that's come into me, but you haven't seen it into your chat box, so I'll verbalize it for you. Um,
Yeah, sure.
the question is that the Husky Wolf example's a few years old now, and how much of the failure that you highlighted there would today's methods catch before deployment, and how many would still slip through the net? So how much has changed in the last few years?
So those the methods. So if we're talking especially about explainable AI, this is something still used a lot. Okay, it's very important. Like again, if we go into governments and even the laws that are being applied on the use of AI when it comes to using AI, all of them require explainable AI. All right, all of them, because like if a model that cannot be understood, a model that we cannot know how the decision were taken, cannot be used for governmental decision, high stake decisions. So that's the first thing. Second, when we're talking about correlation and causation, those are things that some of you might have heard, like because we've been talking about this for hundreds of years. You know, it's a topic that it's never ending, right? But that's the thing; it's never ending because we always have to deal with the patterns and relationship, and we're always trying to understand whether what I'm looking at is a pattern or just a relationship. Because if it's a pattern, I cannot take a decision on top of that. I cannot take a decision just on top of a pattern. I need to take a decision on top of a relationship, something reliable, and this will help me to make a change. So again, those tools are always being used, constantly being used, improved, and so on. But when we are talking about correlation and causation, here we're talking about a methodological approach, right? And this is quite a strong, reliable approach that has been developed over the years. New algorithms are coming in, but the methodology is always the same.
Okay, that's interesting because that you're kind of addressing the next question that I've got, which is about when you come across a new model or data set, what's the first thing you check to get a sense of whether a pattern might be causal or just correlation?
So, thank you for this question. So, the idea is, you see, this is very interesting. Like again, you think about, oh, I need to figure out whether this is there is a causal relationship or there is a just a basic correlation, a basic pattern, and you think that the answer will be in the data. Well, the answer might not be in the data, but you need to. The first thing that I would ask myself is why the data are like this. What is the data generation process behind them? How they came to be, right? And this is something that I have to do all the time with the clients, the people that I'm working with, right? They just imagine they just dump the data on your table, and now you have to figure out things. No way, no way. We need to talk. We need to understand. Okay, I need to know how you collected this data. Why did you collect it in this way? Why you pick this variable? Why there is this variation in the data, right? And this is a matter of either communication or you are the one who collected the data, right? Because you, in that case, can decide, can manage the data generation process.
So this leads me on to thinking about the governance of AI, and
Mm-hmm.
you're kind of talking about human reviewing it. Is there any kind of stronger guardrail within the AI governance piece that you're aware of that can go through and help reduce the failure rates, help to improve and progress this? What type of governance is out there that can help with what you're identifying as a problem?
So, this is a very hot topic, I would say. All governments, international governmental organization are talking about it. The private sector, we see so many examples of this issue, right? Like think about Deloitte last year, the scandal of Deloitte. Uh, so many are, so many private companies are getting into legal issues because of their misuse of LLM, right? And again, when we are talking about liability, the LLM, ChatGPT, OpenAI, whoever, like they are not liable, right? We are liable. And so there are ways, and I'm actually working on this, like developing a framework that will allow people to use AI in a safe way. But the most important principle, I think, is understanding, again, something I mentioned earlier. So the right tool for the right task, right? So are we answering an email? Are we just replying to a simple comment, whatever? Okay. What's the risk associated with using AI in this case, right? Are we working on the final output of an analysis or a final report of some financial documents, okay, that is going to go in the hand of our stakeholders, government, so on? What is the risk of using AI and making a mistake? The risk, okay, so in both cases, we could have the exact same error, hallucination, and name whatever you want to, right? But the thing is that the risk, okay, the risk associated with that mistake is much, much higher when it comes to decision making, when it comes to provide a final report for the stakeholders and so on. So we need to understand when to use that tool, okay, to minimize the risk, because it's not really something that we can predict, right? We cannot predict when the LLM is gonna end up with hallucination. We can do all sorts of things, but again, if even we try to decrease that, and there is just 1% chance, you don't want even 1% chance when you are pushing out the final report for the stakeholders, right?
Can I then think of, because I'm used to being a dean of a business school, and
Yeah.
lots of things which you're talking about are obviously data science related, but they have an implication on the public policy world, on people who make engineering decisions, healthcare.
So,
Also the same thing for business. So I think the question I've got is about the randomized control trial, which looks like it's a gold standard in this area, but
absolutely.
lots of business decisions can't wait to do these RCTs. So what do
Mhm.
you reach for when a controlled experiment isn't possible?
So in that case, obviously, randomized controlled trials are very, very expensive, right? Like they're extremely expensive. Sometimes they are unethical, right? And there are techniques, and actually we are talking about my own field, causal machine learning. Okay, so there are other methodology and techniques and algorithms that can help us to estimate the effect of a program or a policy or a given decision, even when we are dealing with observational data, which are basically non-randomized controlled trials. So really depending again on the available data and the underlying data generation process, we can use, for example, techniques that use time series data modeling, right? So we can observe how things have been over time, and then imagine that you have a time series, and then at a certain point you have a new policy, right? So you observe how the policy has been going on. So you have a KPI, let's say students enrollment or student scores, right? Marks. And what you can do is that this is a technique that it's very interesting, very dear to me, which is called synthetic control. You could build a machine learning model to create a counterfactual, well, that's how we call it, right? A hypothetical scenario, reality, in which that event, that policy, that program never happened. So what you want to do is that you want to create another time series. There is the continuation of the previous part of the time series before the treatment, right? So business as usual. Now, thanks to these two parallel time series, you can estimate the effect of the program. So this is a very elegant methodology, but obviously it requires certain algorithms and certain assumptions.
Okay. So I guess in my mind, I want to simplify one or two things here, and that's
Yeah.
related what I'd say to a practical test. So for a professional who isn't from a data science type background, what type of simple question can they ask of any AI-driven recommendation to help pressure test it? What type of question can they go through and ask
Why?
to make it easier? Always why? Always why?
No, first of all, why? Okay, so first of all, you can ask yourself why, and obviously you can ask the LLM. So when we are dealing with this tool, we also from a purely technical perspective, when we are building tests around our algorithm, our systems, so it's a common practice to build tests to check whether the output is correct, if the system will still work under certain conditions, and so on. So the number of tests from the boom of LLM has tripled. Like now we have to write even more tests because again, it's very assertive, right? So we always have to challenge the LLM. Actually, there are approaches to leverage the assertiveness of LLMs, right? So you could not challenge the LLM, but instead ask the LLM to challenge you, all right? So this is an approach. It's a very simple approach, but actually it works really well. So you have to instruct the LLM to always try to go against what you want or what you suggest, okay, in order to prove itself, right? So it's a kind of a really good way of creating a positive loop, okay, in the interaction. Which obviously takes much more token, more conversation, more back and forth, but that's the only way. And again, even I would always recommend practitioners, especially who are not very knowledgeable of statistical algorithms and everything, like always double check everything with someone who has obviously knowledge about this, because again, LLMs, they tend to provide you with the most common, most obvious, most used solution, right? Because they were trained on that. Okay, what is online, what people are saying online, okay, because it was trained on online data. They will provide you with that answer. It might not be ideal, okay, for you. Most of the time, it might work, okay, it might be good enough. But again, sometimes you need specialized techniques, specialized tools that the LLM will never naturally, by default, suggest, right?
Very good. Well, thank you very much. I've asked you quite a few questions. I can't see any
Pleasure.
other question in the Q&A. So what I'm going to do, we are close to the end. I want to just share a few last slides, which summarize, from my perspective, your presentation, and then move on just to explain a little bit about where people can get information about the program and about the school. So these are my takeaways from linking your presentation, Dr. Hammad, to the AIT School for Professional Intelligence and our programs. Is number one is looking at correlation not being causation, and that a real pattern can rest on a false relationship. So that's my main kind of takeaway from that aspect of your talk. The second one is about the confounder, this term, which I think really useful to go through and understand, is about the way that machines see the pattern, but it can't always see the process that created that. And then about the selection hides in the data. I thought that was really quite fascinating about how the healthcare case that you went through and presented, the need to go through and ask what generated that data, to go through and get a little bit more of a deep dive around that issue, and the way that LLMs are not exempt, and that the danger, you use this term, confident wrongness, that model can't detect. So you highlighted some of the advantages and disadvantages of AI today, particularly looking at LLMs. And I like the title about decision making for AI. And thank you very much, Ahmed, for being the fourth of our masterclass speakers.
My pleasure. Thank you.
This for me is about what can you do that AI cannot, and you have to ask why. The next session for the masterclass will be announced in due course. For those of you who are interested to learn more about AIT Spin, either through the website or the flyer, this is the QR code that you can go through and scan quickly. But for tonight, we are almost at our 1 hour time limit. So I'd like to thank Dr. Hammad one more time. Ahmed, thank you for your time and your insights into AI, LLM, and also about decision making and AI. I look forward to seeing you more on the program in the weeks, months, and years ahead. Thank you very much.
Thank you very much. Thank you, everyone.
And thanks to the audience for your time here tonight as well. Take care. Bye-bye. Thank you. Thank you very much.